Good morning, students. So today we start the first chapter of Pharmaceutical Chemistry 1 of Diploma Pharmacy first year, that is acid, bases and buffers. This is the part 1 of this video. Acids and bases are defined by the four main theories. First one is the traditional theory, which is a very common theory. Second is the Arrhenius theory. Third one is the Bronsted and Lowry theory. And fourth one is Lewis theory. So we will discuss these theories further in detail. First one is the traditional theory. According to this theory, acids are the substances which converts blue litmus paper to red. Okay, so they generally convert the blue litmus paper to red. They have the pH less than 7 as shown by the first figure. Okay, so all the substances having pH less than 7 are the acidic substances like urine, black coffee, tomato juice, orange juice, lemon juice, and the most acidic one is the gastric acid. Third property of the acid according to this theory is acid have the sour taste and they react with the bases to form the salts and water. Example of the strong acid is hydrochloric acid. Then the base. Bases are the substances which converts red litmus paper to blue. They have the pH greater than 7. Again, this figure shows that all the substances having pH greater than 7 are the alkaline substances, basic substances like urine, black coffee, like seawater, baking soda, milk of magnesia, ammonia solution, soapy water, and the most basic one is bleach. They have the bitter taste and they react with acids to form salts and water. Example is the strong sodium hydroxide. Then the second theory is given by the Arrhenius in 1887 in his famous theory of ionization. According to him, they define the acid and bases according to their formation of ions when dissolved in water. This theory is also known as Arrhenius theory of ionization and the electron dissociation theory. According to him, an acid is a substance that releases hydrogen ions when dissolved in water. Example is hydrochloric acid, which is a stronger acid, and the acetic acid. HCl reacts with water and gives the H positive and the Cl negative ions. So the release of H positive ion shows that it's an acid. Okay. Second is acetic acid. Sorry, here H is missing. CH3COH. When dissolved in water, it gives acetate ion, that is CH3CO negative, and the H positive. Again, H positive shows that it's an acid. And then the second thing is how it shows that it's a stronger acid or a weaker acid. Actually, the property of acids are due to the H positive ion. An acid which releases larger concentration of H positive ion or high degree of ionization is called the strong acid. Okay, so H positive shows higher degree of ionization. In case of HCl shows high degree of ionization, so it's a stronger acid. Wherever the CH3COOH acetic acid shows the degree of ionization less, so it is called weaker acid. Okay. Then a base is a substance that furnishes the hydroxyl ions when dissolved in water. Okay, so this is the second theory. This is the theory given by the Arrhenius, that base is a substance that can release a hydroxyl ion when dissolved in water. Example is sodium hydroxide. Sodium hydroxide, when dissociated in water, when dissolved in water, it gives the Na positive plus OH negative. So again, the degree of ionization is greater in sodium hydroxide, so it's a stronger base. Whereas ammonium hydroxide, when dissolved in water, dissociated to give ammonium ion plus OH negative. Here OH negative is not completely dissociated from ammonium hydroxide, so it's a weaker base. Then neutralization reaction. Arrhenius theory shows that when acid and base react with each other, they form the salt and water. So it is commonly known as neutralization reaction. Here NaOH is a base, HCl is an acid. When they completely react, they completely dissociated and form sodium chloride, that is salt, plus water. So there are some limitations of this theory. First one is in this theory, water is very essential. Okay, so hydrochloric acid is regarded as an acid only when dissolved in water. Okay, but not in non-polar solvents such as benzene. or when it exists in the gaseous form. So it doesn't explain the acidity or basicity of non-aqueous solvent. Okay. Third is, Arrhenius concept could not explain the basic nature of substances like the ammonia or the sodium carbonate, which do not contain OH negative ion. And the acidic nature of substances like BF3, AlCl3, carbon dioxide, sulfur dioxide, which do not contain H positive ion. So these are the limitations of Arrhenius concept. So the third theory was introduced. Okay, this theory it was given by the Danish chemist J.N. Bronsted and Thomas Lowry, an English chemist, in 1923. They proposed new definitions. According to him, acid is a substance that can donate a proton. It is also called as proton donor. Whereas base is a substance that accepts a proton. It is also called as proton acceptor. So here, acid, when reacts with water, donates its proton by forming Cl negative ion. So it's an acid, whereas water in this case accepts a proton, and so it's a base. Okay. In second example, base is a proton acceptor, which shows that it is a proton acceptor. Like when ammonia reacts with water, NH3 accept a proton and form a base, and form a NH4 positive ion. So it's a base, okay? Whereas the water in this case donates a proton, and so it's an acid. Here again, a strong acid has a larger tendency to donate a proton, okay? Like HCl in this case has a larger tendency to donate a proton, so it's a strong acid. Similarly for vice versa for the base. As can be seen from the previous two examples, water is capable of acting as both an acid and a base. So any substance that can act as both an acid and a base, it is said to be amphoteric. So water is a very good example of amphoteric nature. Then conjugate acid-base pairs. Acid and bases actually exist in pairs called as conjugate acid-base pairs. Every time an acid donates or loses a proton, it becomes its conjugate base. Like an example, acetic acid plus water. Okay, here acid donates its proton and forms the acetate ion. So acetate ion is a conjugate base of acetic acid. Second example, where base accepts a proton, it becomes its conjugate acid, like ammonia. In case of ammonia, reacts with water, ammonia accepts a proton and form the NH4 positive ion. So ammonium ion is a conjugate acid of ammonia. Last theory is the Lewis concept. Gilbert Lewis focused on the donation or acceptance of a pair of electrons during a reaction. So they give a more general definition of acid and base. According to him, base is an electron pair donor and acid is an electron pair acceptor. Okay, so Lewis acid is shows that any substance such as the H positive ion that can accept a pair of non-bonding electron, it's an electron pair acceptor and it's a Lewis acid. Whereas Lewis base is any substance such as the OH negative ion that can donate a pair of non-bonding electron. Okay, so Lewis base is electron pair donor. This example shows when ammonia reacts with BF3, ammonia loses its pair of electrons. They donate its lone pair of electrons. So it's a Lewis base, and BF3 accept this lone pair of electrons. So it's a Lewis acid, and they form an addition compound. So reaction of a Lewis base with the Lewis acid produces an addition compound. Acid-base reaction in the Lewis concept is the formation of a coordinate covalent bond, and this process is also called coordination or neutralization reaction. So what are the advantages of this Lewis concept? This concept also includes those reactions in which no protons are involved. Okay. Second, Lewis concept is more general than the Bronsted-Lowry concept and the Arrhenius concept. Okay, so like in Bronsted-Lowry concept, acid-base behavior is dependent on the presence of one particular element or the presence or absence of a solvent. So in this case, it is not like that. Third, the Lewis approach is of greater value in cases where the protonic concept is not applicable. Okay, example in reaction between acidic and basic oxides in the fused state. Disadvantages of this theory is it doesn't directly classify acids and bases according to their strength. Okay, so the acidity and basicity of compound depends on type of reaction. Hence, order of relative strength cannot be fixed. Generally, acid-base reactions are very rapid, but Lewis acid-base reactions are slow. So this is also a limitation. Second, we will discuss the various official compounds mentioned in your syllabus. First one is the boric acid, hydrochloric acid, strong ammonium hydroxide, and sodium hydroxide. In this part one, we will discuss only the acid part, that is boric acid and hydrochloric acid. And the second part of this video, we will discuss the next two compounds like strong ammonium hydroxide and the sodium hydroxide. So boric acid. The chemical formula of boric acid is H3BO3. Okay. The molecular weight is 61.83. The synonym of a boric acid is orthoboric acid and the boracic acid. The method of preparation, which is generally a laboratory process, is boric acid is prepared by boiling the solution of borax with 20% sulfuric acid in the presence of water. The solution is filtered and crystallized. The crystals of boric acid are separated and dried at room temperature. Okay, so here borax react with H2SO4 plus 5 water. It forms the H3BO3 plus Na2SO4. Next are the properties of boric acid. Physical properties, it's a white crystalline, colorless, shiny plate or powder, odorless in nature, okay, soluble in boiling water and in 95% ethanol, freely soluble in boiling water and also soluble in glycerin. Chemical properties, it reacts with turmeric paper, boric acid turns into brown color, okay. The second chemical property is reaction with glycerin. Boric acid reacts with glycerin, dissolves and form the glyceroboric acid. Third chemical property is their action on heating. When on heating, it loses water and it converted into metaboric acid, HbO2 plus water. When it is heated at 160 degrees Celsius, it forms tetraboric acid, which is H2B4O7. And up to red hot, it forms the boron trioxide. It loses all its water and forms the boron trioxide. So these are the reactions which it shows on heating. Next are the various uses of boric acid. Boric acid is a local anti-infective. Second uses to maintain the acidic pH medium in medicament. Third, it is used in the preparation of buffer solution, and it is also used in ophthalmic preparations. It is used as a dusting powder and are also used in the preparation of ointments. Storage, it should be stored in a well-closed container at a cool place. So these are the method of preparation, properties, uses, and storage of boric acid. Next, acidic substance we will discuss is hydrochloric acid. The chemical formula of hydrochloric acid is HCl. Molecular weight is 36.46. Synonym is spirit of salt, muriatic acid, acidium hydrochloricum. Method of preparation, when concentrated sulfuric acid react with sodium chloride, common salt, they generally heated in a cast iron pan in salt cake furnace. It forms hydrochloric acid and the sodium hydrogen sulfide. Next are the properties. Physical properties, it is a clear, colorless liquid, fuming liquid with the pungent odor and miscible with water and miscible with the alcohol. Chemical properties are, it is dissociated into hydrogen and chloride at 1500 degrees Celsius. So HCl completely dissociated to form H2 and Cl2 when heated to 1500 degrees Celsius. Second chemical property is it forms dense white fumes with ammonia. Ammonia react with HCl, they form the fumes of ammonium chloride. Third, react with the various metals. Hydrochloric acid react with sodium, gives sodium chloride and evaluation of hydrogen gas. Fourth chemical property is reaction with the alkalis. Hydrochloric acid reacts with sodium hydroxide and gives the sodium chloride and water. Next one is it neutralizes the oxides and even the hydroxides. Okay, like magnesium oxide react with HCl and forms the magnesium chloride and water, salt and water. While carbonate and the bicarbonate decomposed with evolution of carbon dioxide. Like sodium carbonate react with HCl and forms a sodium chloride with evolution of carbon dioxide plus water. So these are the properties of hydrochloric acid. Next are the uses. Hydrochloric acid is used as an acidifying agent and a pharmaceutical aid as a solvent in industry. It is used for the manufacturing of basic pharmaceuticals, so it is a pharmaceutical aid, and also as a reagent in laboratory. It is also used for the purification of common salt. It reacts with NaCl. Storage. It should be stored in glass stoppered container with a temperature not exceeding the 30 degrees Celsius. Sorry, here it is 300, but it is actually 30 degrees Celsius. So I hope there is no doubt up to this. And the next two compounds and the buffers we will discuss in the part 2 of this video. Thank you so much.